Okay, well, ladies and gentlemen, colleagues, visitors, those of you who don't know me, I'm not the principal, which it said on the invitation. The principal sends his apologies. He's in India at the moment. I'm Nigel Brown. I'm the Senior Vice Principal of the university. And it's a great pleasure to welcome you all to this inaugural lecture by Professor Arvind. Now, it's a particular pleasure to welcome Arvind's wife, Rupa, and his children. His colleagues who are attending today for the workshop on speckled computing in healthcare, and our other visitors. Now, as I'm sure we'll find out during this lecture, speckled computing is a fascinating concept which has application in a large number of areas. And Professor Arvind has been a leader of a consortium of experts in this, what's called a radical new concept in information technology. And associated with his promotion to a chair, the university has been pleased to create the Centre for Speckled Computing, which Arvind heads. Now, I'm not going to say anything more about the technology, firstly because I don't fully understand it, and secondly, the expert is about to tell us about it. But let me tell you a little bit about the expert. Firstly, he trained in electronic and electrical engineering at King's College London, and subsequently worked at the GEC Research Centre and at Carnegie Mellon University, before coming to Edinburgh as a university demonstrator, a relatively lowly form of staff life in those days, I guess, in 1987, and he's been here ever since. He's currently also the visiting professor at the University of California, Berkeley. He has a large number of academic and commercial collaborations and a large amount of grant income from research councils, the European Union, and other research funders, including companies. He has well over 100 publications and communications and has led for several years the Research Consortium for Speckled Computing, bringing together computer scientists, electrochemists, physicists, and electronic engineers across 5 UK universities. In what spare time remains, I'm told that he enjoys reading, travelling, and watching cricket. For those of us who follow the game, neither England nor India provide particular entertainment at the moment, but at least we can take comfort, Arvind, in they're better than Scotland. Now, it's entirely appropriate, I think, that we have an inaugural lecture on informatics in the first month of 2012, because of many, as you know, this is the year that celebrates the centenary of Alan Turing's birth. So I'm very pleased to invite Professor Arvind to give his inaugural lecture on speckled computing. Arvind.
Thank you very much. Thank you. Welcome, ladies and gentlemen. The idea of the inaugural lecture is to make it accessible, so that it reaches as wide an audience as possible, and I try to do that today. And I might fail sometimes, so I'll try and keep it as general as possible, without any graphs and equations, etc. So before I start, I want to make a few acknowledgements, because the speckled computing, or in its previous incarnation, as the Research Consortium in Speckled Computing, started off as a collaboration between several universities, 5 universities to start with. And I think I'd like to acknowledge the support and the wonderful work and ideas which came from all these collaborators. So there was the University of Glasgow, the electronic engineers there, led by Professor Ian Thane, and then there was University of Strathclyde, led by Professor Robert Stewart, and then there was people at Napier University, at least in the first half of the project, led by Professor Ben Pector, and then there were people in St Andrews University, and there was Alan Miller, at the time in the School of Physics. Since then, he has moved on to higher things at Heriot-Watt University. And there was Thomas Krauss, who was the professor there. So it was these people and the and the teams which came together was extremely important in the development of speckled computing. And in the way it was organized, we had a research advisory board, and we were very fortunate that we had people involved in it who gave their time quite unsparingly. And the two Johns I'd like to thank, there's John Campbell, QC, should be here somewhere, yeah, there he is, who was the chairman of the Research Advisory Board, and John Gray, who has been sort of advising us, mentoring us right from the start. So thank you all for that. But most importantly, it's also all the research students, the collaborators, the members of our research group at Edinburgh, too many to name individually, but who have sort of stayed with us for quite a long period of time. And thank you very much for all the fantastic work. And a person who's in all the chaos surrounding us, who has sort of held things together for us, who has stayed calm in all this, has been Charmaine Leach. Where is she? She's there somewhere. There she is. Okay. Thank you. And it's been a multidisciplinary collaboration, so that brings together lots of computer scientists, electronic engineers, physicists, electrochemists, and we needed to learn each other's language, and that was quite an experience in itself. And now, increasingly, we see the application of speckled computing in lots of different areas. In fact, today we had a workshop which looked at the application of speckled computing in healthcare. And thank you to all these collaborators who have given their time, and we've learned a lot from them. So thank you all. Thank you to EPSRC for having the vision to fund this, and even before that, Scottish Funding Council for doing that, and a number of companies who have been funding the center, and also my colleagues at the University of California at Berkeley, where I visit. I should be visiting more frequently, but I visit occasionally these days, but thank you to them. And of course, a number of EU projects that we are involved in. So that's the story. And a person I really need to thank for organizing today's event is Marjorie Dunlop, who, despite an accident, has done very well to make sure that everything was in place in good time. Marjorie's not here. Thank you very much, Marjorie. Okay. Now, the internet, as we know it, seemed to affect every facet of our lives these days. And in the growth of the data in the internet, the majority of the first 50 petabytes of data which is available on the internet were first captured and created by human beings. Whether it was archival data, which came out of these printed cards, old teleprinters, or more recently through typing on the keyboard or pressing a button to take an image, or touch screen, or the barcode reader. There's huge amounts of information which has been gathered on the internet at the moment has actually come from created by human beings. By the way, a petabyte is sort of 1 followed by 15 zeros. So that's a number of bytes. It's a large number, whatever it is. But if you actually look at and that is kind of changing in character, because the amount of data which is being produced by sensors, so the kinds of sensors. So the Large Hadron Collider in the top left is a sensor, and that produces about 2 petabytes of data in each experiment, for instance, or the data from the meteorological sensors that you have, or the data from large arrays of telescopes. So that's the very large array telescope that you have, or from biological experiment when you're doing the microarrays. So all these are sensors of some form or the other, and increasingly they're kind of producing data onto the internet. But those are not the kind of sensors I'm concerned about. The kinds of sensors that I'm concerned about is very much been inspired by a scientist, Mark Weiser, who sadly died quite young, who enunciated this in 1991 when he was a scientist at Xerox PARC. Now, Xerox Palo Alto Research Center was this wonderful nursery of ideas which came out of that, which sadly they didn't commercialize very well, but that's a different story. And Mark Weiser said in 91 that hundreds of computers in a room could seem intimidating at first, just as hundreds of volts coursing through wires in the walls did at one time. But like wires in the walls, these hundreds of computers will come to be invisible to common awareness. People will simply use them unconsciously to accomplish everyday tasks. So in a sense, that was an inspiration for me at the time as to how will one enable this? And there have been a number of projects, and today, for instance, somebody referred to the disappearing computer, and that was one of the ideas which came out as a European project sort of 10 years ago, I think it was. So I'm more interested in this. It's how can we make these computers small enough and at the same time with sensors in them, which would be unobtrusive, would actually disappear into the environment, as it were. So the vision is that can we endow persons and objects with sensing, processing, and wireless networking capability? And the wireless networking is important if it needs to be unobtrusive. We don't have a bird's nest of wires trailing all around us, so we don't want that. So, and the very important idea here is that we want to link the sensory world, the sensory data in the physical world that we inhabit with the digital world of computers. So we want to bridge these two worlds, the physical and virtual worlds. So how do we do that is the question. And how does this fit in with the future of the internet that I spoke about? Because one of the limitations in the internet, as it was in the previous, when it was first devised or designed, if you want to call it that, was that we were reaching the limit of how many unique names that we could have for these computers. Okay, and that fortunately has been overcome by having a new internet protocol, which is called IPv6, which will support more than 35 trillion separate subnetworks, and each subnetwork in turn will connect 1 million devices. So we have, at least for now, a large enough space that we can name all these devices uniquely. So we're moving towards a world of connectedness between people and smart objects. So I've put smart in inverted commas because it's an abused term. So what I mean by smart in this context is that it's context sensitive. That is, it knows something about its environment, and also its location is a very important property to have in some cases. So it's context sensitive and it's location aware. So that's the vision, to be able to take these almost everyday objects and then endow these everyday objects with the capability to sense, process the data that you sense, and then network with other such devices, so that in turn connects to the internet. So what you have is almost like a fractal, where you have lots of networks, subnetworks, in terms of subnetworks. So it recursively forms this network. So that's the way we envisage the future internet would look like. Now, so people have been talking about this, and other given names such as Internet of Things, for instance. That is, there are these things which are connected to the internet. That's not a term which I use, because I'm aware of the Internet of Things. And when first the Internet of Things were defined by people at Procter & Gamble, it was mainly for for being able to use RFID tags. So RFID is radio frequency identifying tags, which could help in the supply chain. So if you imagine Procter & Gamble is a company which manufactured a number of these household goods like your pastes and soaps and shampoos and various other things, the ability to actually track these was something that they were interested in. So RFID itself is quite limited in what it can do, but as you will see later, we were a bit more ambitious than just RFID tags. So that wasn't a term that I wanted to use early on. So you need to be aware that there's something called the Internet of Things, which is kind of converging with our ideas of what speckled computing should be doing. So they're sort of coming together because they need each of these nodes on the everyday things to be quite intelligent in the way that I say it. What I really wanted to show you is that there are three things which you would find these terminology being used, that you want to be able to connect anything at any place and at any time. So even if it's on the move, you need to be able to connect all these objects together. So what are these specs? So these specs are miniature programmable semiconductor devices. I think the word programmable is extremely important here because it's the behavior that you invest in these particular devices which differentiates one application from another. So they are programmable. And there are three functions that they have. They have sensors that they can sense, and depending on the kind of application, you might have different sensors. They can compute the data that they sense, and they network wirelessly with other such devices. Okay. And we want them to be autonomous, preferably with rechargeable batteries, and even better, if they can scavenge this energy from the environment. For instance, they could have a photovoltaic cell which is tuned to, say, internal lighting, and in which case you don't have to remove the battery and charge them again. Okay. And we also assume that these specs are non-static, that is, and also that they are unreliable, because if you produce them in large numbers, you can't expect them all to be working all the time, in which case you have, the idea would be that you want to provide a certain service, a certain quality of service as it's called, and how can you ensure that you have sufficient number of specs which provide this quality of service, knowing that you have a certain attrition rate, that is, over time some of these specs would fall off, as it were, but you still need to provide the service. So one can think in terms of a half-life of these networks. So that's the vision. And tens, if not hundreds, of these specs collaborate as dense programmable networks. Again, it's the programmability of this network is extremely important. And it's not the individual spec, but it's the network that it constitutes. So specs may come and specs may go, but the Specknet, the network should go on forever, as it were. So, and what you have here is that each of these specs senses the data and it processes the data locally, so you have partial results, and then it shares these results with its neighbors in order to solve a much larger problem. And the idea here is for you to be able to extract information from the raw data that you have, and being able to do it in situ, being able to do it at the edges. And this might involve actually performing some actuation. That is, you sense, you process the data, and then you act on the data. And you'll see some examples of this in the future. So you might think of this as being sort of a fine-grained distributed computation. Just as you have a network of computers that we have at the moment, they form a grid, as it's called, and they are able to solve collaboratively a large problem where data is stored in each of these individual computers. Similarly, we are able to do this on a network of specs. The difference being that the resources that you have available in the specs are meager, are minute compared to the resources that you have in the computers. So you might have kilobytes of memory, 8 kilobytes of memory, whereas it's customary, it's normal to have megabytes, that is 1 million kilobytes of memory in these things, or even gigabytes of memory in these things. So it's a matter of scale here. And also, they need to be self-powered. They don't have a plug in the wall that you could go with. So you have these small batteries, and you need to power them off these batteries. So the challenges are many. So the vision is that just as you have different telecom services, you might be familiar with, for instance, getting a broadband internet or your video calls or TV channels these days, that in the future you would get data from these sensor networks that are shared with people. And that's the vision, that it's a telecommunication service which is provided along with lots of other services on what is known as an IP network. So that's the workhorse which actually does all this, does this for you. So over the years, we've developed a family of these spec devices. So what I'm going to do is go historically around this and show you some of this. So on the top left, you see the first device that we designed, which has a 2.4 gigahertz radio. It has 8 kilobytes of memory, and it has a very slow processor on it. And the idea being that the same functionality that you have there has been reduced to that size there, because it's going to have a small battery in there. So that was the first one. And what you have next to that here is a microserver, which has some beefier resources in that. It has a 32-bit ARM processor. And that later, and it actually ran a Java, it's called a Squawk, or the Java virtual machine in there. It's a virtual machine which requires quite limited memory. And we were able to demonstrate this to Sun Microsystems, and that became the Sunspot. That was the basis on which the Sunspot was developed, which was distributed by Suns to a lot of laboratories and schools and various other places. So that work was actually done in our labs here. In this one, you can connect up to 4 sensors. Depending on the application, you can connect 4 sensors, and you can build up various applications based on that. And we had large arrays of these as test beds that you can run sort of routing algorithms and various other algorithms. And they had a backplane so that you can calculate, you can measure the power consumption and various other attributes of that particular algorithm that you're running there. In a kind of a batch mode. So you run these overnight and you collect all the information and you have a good understanding as to what's happening. So that's the basis for this. So going round, what you have on the top right is the Orient spec. And in this case, what you have is a spec with 3 particular sensors in there. So it's a 3-axis gyroscope, a 3-axis magnetometer, and a 3-axis accelerometer. And you'll see more of that later. And the idea here is that we identified a large class of problems where we felt that wireless sensor networks could play a part, could solve certain problems. And so that's been optimized for that particular class of applications. And then you have the bottom right is a device which can scavenge energy. In this case, it's a photovoltaic cell, so that you can do environmental monitoring using these devices. And what you see in the middle here is a device which is called a Respire, which is a device which can be worn as a wireless patch and can measure the respiratory rate and flow and also movement, etc. So there's a class of problems that is addressed, which is in healthcare, and you'll see more of that later. So these are some examples of spec devices that we've developed over the years. Now, I mentioned motion capture. And the reason we came to motion capture was because the existing solutions at the time, so this was in 2005, were one of the following. You could either have, what is happening on the top right is joint angle sensors, which are potentiometers, which can measure the angle. And as you can see, that's quite cumbersome. It's very bulky, and it hinders free movement. Or you can have something like this, where you have these markers on the person, and then you have 8 cameras in a studio, which is trained on the person, and you're able to get the images, the videos of the person from different angles, and then you put them all together, and you get a 3D motion capture of the person, in this case, breakdancing. So it's very much dependent on the lighting conditions. So you might have occlusions if you're trying to get more than one person together, and you solve that by increasing the number of cameras, which in turn increases the number of processing that you need to perform. You have limited coverage. Given that you're in a studio of this size, the active area is a very small volume of 3 or 4 meters cube in the center. And it's limited coverage volume and your studio-based infrastructure. Or you can have one of these, which are inertial sensors with wires connecting them, and you have to wear this suit, and what the suit does is hides all the wires. So this was the state of play in 2005, when we thought that we could do better than that. So the idea was, the wish list here was the ability to capture, analyze, and understand motion in a way which is fully wireless, and being able to do it in real time, and in a fashion in which the person could interact with this, which is easy to use. And the idea was that if we could do this in an inexpensive way, then we can sort of banalize this technology and democratize its usage. So that was the wish list there. You should understand that in order to have a motion capture studio, it would cost at least £30,000 just to get the cameras, and then there are certain running costs involved in running a studio. So it's an expensive business, and if you want to hire some time in the studio, it costs you about £800 an hour. So it was an expensive business actually doing motion capture. So here we have Paul McEwen, who was then with us as a researcher. I'm glad to see that he's in the audience somewhere. So what you'll see is Paul actually moving in front of the camera. And then what you see at the background, in this very room, as a matter of fact, is the data going in real time and animating an image in a commercial animation tool. Okay, so that's what you see here. And what you will see is this was done in 2008. This was filmed in 2008. And you can see that the motion of the person is captured in real time, and that in turn animates the figure that you have, the virtual figure. Okay, and the idea was, okay, that looks interesting, and can we sort of see where we can actually take this? Can we sort of apply this in different areas? Now, as you can see, I haven't gone into the technical details for this, but there's a lot of work which went into coming up with new algorithms which can process the data in situ on the devices themselves. And what goes to the outside world is the orientation of that particular limb in 3-dimensional space, which is then used to move the virtual characters. And we thought that, well, some of the people who might be interested in this would be the animators, for instance. And the idea is the analogy with desktop publishing. So, for instance, in the olden days, if you wanted to publish some material, then you'd come up with a manuscript, take it to a print house who would then employ typesetters and who would print the document and then give that back to you after 2 or 3 iterations of proofreading, etc. Okay, but with the advent of Adobe software and laser printers, you're giving your power in the hands of the person themselves. They can sit at the desk and produce a document which is of sufficient quality that's accepted as norm these days. Same way, could we provide this kind of capability of an animator sitting at the desk and producing animation real time? Or could we, for instance, perform remote actuation? Like, can we have a robot which is remote, and can we control the robot? Or teach a new behavior, for instance, rather than program all the details of the robot, where it mimics, to start with, the human motion, and then has a learning algorithm in there so that you can learn new such behaviors. Or could we put this on golfers, for instance, and try and analyze a golf swing on the golf course and give them feedback? Or could we sort of use this to animate, say, an avatar, in the virtual world, where you have simulations and you can combine real players with kind of virtual players, and that's what I'm going to show you first. And again, this is Paul McEwen. Although you don't see Paul McEwen, you'll see his certain maneuvers. I'm not going to tell you what it is. So what we have here is a virtual world, and this is an avatar, and then you're able to invest this avatar with motion by wearing these devices on the person. And you can do this in real time. So you can interact with other such avatars who are also moving in real time. Or it could be a training program where there is a certain task that you need to learn to do well, and you are interacting with these avatars in the training program. So in this case, he's going to do something interesting, I'm sure. There he is. So he's showing off his somersault. So here's an example of how you can capture such motion. And I mentioned the animation. So that's an obvious place where we can take something like this. And so Red Kite is a company in Edinburgh where it's an animation company based in Leith. And we went to them. And this is an example of something that they produce. So what you see in the inset there is the human, and this is the image that you see there. And this is being captured in real time. Having said that, when it's put together, there is a bit of manipulation which takes place. So this is a character called Imp, and which is owned by DC Thompson, based in Dundee. And I believe it's a popular TV program somewhere. And what you see is that the motion made by the person here is quite exaggerated in terms. And what you see here is the merging of these two in the final product, if you want to call it that. And he's asking him to go away. The imp is not terribly happy. And of course, all the eyes blinking had to be post-processed. And that's where you see the jump. And then he takes this walk, which was a very exaggerated walk by the person because of the relative sizes of their legs. Okay, so that's an example. And that was put together in 3 hours where with the animator actually working with it, interacting with it. So you're putting control in the hands of the animator, which is extremely important because, I mean, look at history of animation. Animators like to understand the medium with which they work. And in some way, they lost control with all the digital animation, which can actually come back to the animator now. So we felt that was quite a useful contribution to make. Now, this is another example where we worked with a PhD student, Vangelis, appropriately named a music PhD student. And another was a dancer, flamenco dancer from Edinburgh College of Art. And what you'll see here is a performance in real time, a performance where you produce the music which normally accompanies a flamenco dance, being produced by the motion of the dancers. So you have the castanets, you have the clapping, and you have these various musical instruments which accompanies flamenco dance. But in this case, the dancer herself produces the music. So it's an interesting question. Is she... let me not preempt that. So have a look at this. This is Vangelis and Maria Dima, those things, Marisa. And what you see in the inset is the motion capture in real time. And this was filmed in space next door. And what you should really appreciate is the very low latency with which you capture the motion and perform all the computation in order to do it. Okay, there's more of this, so in the interest of time, I'm going to truncate it here. Okay, and here are the papers which were published in this particular work, and these were the people who are kind of involved in this work here. Right, I mentioned the golf swing, and the golf swing is an interesting example because the biophysics of the golf swing is well understood. There's been a number of physicists who seem to have been good golfers as well. And you can treat the golf swing as a double pendulum, where one arm of the pendulum is your two hands here, and the other is a golf club. And it rotates about the axis in the middle of the shoulder here. And we were able to, for instance, put a device on the golf club, and you can then analyze the plane at which the golf is swinging and be able to demonstrate this in real time to the people. Now, this is quite useful because you don't do this, although it shows as if you're doing it in the lab, you can actually do it in the golf course and see whether you're swinging in the plane, which is one of the important things. And then you can have sensors on the shoulders and the upper arms so that you can analyze the angle between the various parts of your body and see how you can correlate that with the goodness of the swing or otherwise. Okay, and the idea here is that you don't do it just in the lab, but do it in the. That's my only time I went on a golf course. I'm not a golfer, and you can take this data and send this data via the mobile phone to that. An example of this is something like this. So, again, this is the anywhere business of Internet of Things, that you should be able to take the data and then present the data in real time onto your mobile phone. And you have lots of data of this form. There's too much data, as a matter of fact. It's a question of how do you extract this data and present it in a form that is useful for the golfer. You can take this tango dance, for instance, and this was done, I see, by Alkis Valtazanos, who's a PhD student here at the back. And the idea here was, can we get two bodies to interact with each other and then capture that motion? And in this case, you have things like the angle between the chest of the two bodies should be maintained during the dance. Now, this might seem like a diversion, as it were, a bit of fun. It is a bit of fun. But you are trying to understand how you can capture the motion not in a single body, but bodies which are interacting with each other, which is quite important in this case. And that was published in those conferences. And then we worked with Martine Verhoel, who should be in the audience somewhere. Is Martine there? Martine? Oh, there she is. Yes, thank you. We haven't seen Martine for a while because, as you will see, So the idea here was, can we sort of analyze the control of motor control skills in 4-year-olds as they develop? And that is important because being able to do it with technology which in the past, the way it was done is you had a person sitting down and noting how they kick or how they throw the ball, etc. People have tried to bring them into a studio and then put these markers on them and then place a 4-year-old in this motion capture studio and ask them to behave normally. Of course they don't. So can we put this on devices on the children and do this so this work was done in Portobello, in a nursery in Portobello by Martine and her collaborators. And the idea here was, can this be, the term that they use as being ecologically valid? That is, you want to collect the data in the environment where the children are playing. So the kind of data, normally we don't animate this, but the kind of data you would get is they have these devices on them, and you find out how they throw and the angle of throwing and whether they are freeing their shoulders, because as they develop more, they tend to free their shoulders. So that's something that you're trying to capture. The angle between the wrist and the angle between the elbow and the angle of the shoulder are the kind of quantities that you would like to measure. And you're able to do this in the environment in which the children are. So here's an example of how this technology can enable research in other areas that wasn't possible before. And we took this further into clinical gait analysis. Now, gait analysis is something that you need, for instance, for a person either has an artificial limb being attached and you want to understand whether the gait is not abnormally affected by the thing. So you want to tune the prosthesis in such a way that you have a normal gait. Okay. And the way it's done is they come to a motion capture studio, they attach with all these devices, and then you have 8 cameras trained in them. They walk up and down, and what you do is you get data for the person for that snapshot of 20 minutes that they're there. You don't know how they perform at other times. How do they perform when they're climbing a stair? Or how do they perform when going up a slope? Or how do they perform in the morning when they are fresh, or in the evening when they are tired? Okay, so what you want is comprehensive data on these people rather than a snapshot. Okay, so this is something that we did in collaboration with the clinicians in the Gait Center. So what you see, I think is very clear. So you mount these at these points here, and here is an example of something like this. And in this case, we also had these markers so that we could compare the traditional way that it's done in a studio with our method, and that's what the graph that you see sort of indicates that. So what you're doing is you're freeing motion capture for gait analysis from the studio by being able to do it in the environment which these people would normally inhabit. And having understood how we can analyze the gait, it seemed like an obvious thing to do. You know, can we go from human gait to robot walk? You know, can we sort of use the data that we capture from the human gait to use this as a means of teaching, in inverted commas, robots how to walk? And the robot walk has always been a challenging problem, and one result of this has been this. So this is a Condor robot, and it's quite old by current standards. And what you should also understand is there has been no human intervention here other than providing the motion data from the human. So it is a kind of a walk, you might say. It's more like a Boris Karloff kind of walk. Actually, when I was doing this, I went back and actually looked at some of those films. I think he was a very good actor because I thought he did quite similar to that. I wanted to get hold of one of these and show it to you, but I was infringing on copyright and various other things, and I wasn't sure I wanted to do that. So that's one way in which you can invest new behaviors to these robots based on motion capture from the human. Or you can go one step further and say, can I control these robots remotely? You know, And this was done in collaboration with some researchers at Berkeley. So there's a PhD student in Berkeley who came over, spent a year with me here, and then we did some experiments thing. And the idea here is that you do the motion, you're able to control these things. So I'll show you some examples of these teleoperations. So this is being done in real time here. So as you can see, the robot mimics the behavior. So you're measuring all the angles between the various limbs, and you're transmitting that to the robot, and the robot is actuating these. So all these motors are turning by that particular angle. Doing that. And you can go one step further and do a few more complex operations. And in this case, things like reproducing the motion of waving arms, for instance. And I was going to show you one more, which is standing on one leg. And the other important thing to recognize here is that this is not a closed loop system. In other words, there aren't sensors on the robots which can correct any local imbalances in case they were to fall. That would be a step further, for instance. So here's an example of this walking. So, and these were published in conferences. So that kind of gives you some idea of what we want to do there, that area. Now, one of the things that we tend to do in this kind of work in the motion capture is be able to put this on the various limbs. And the question arose, can we sort of wear this as a patch below the ribs here and be able to measure the rotation of the chest wall, for instance, rotation of the abdomen in this case. And turned out, yes, we could. To cut a long story short, what we were able to do is be able to demonstrate that the effort that one spends in rotating the chest wall was a good proxy for the respiratory rate and the flow. And so what you see here is that if you were to breathe, then you have a nasal airflow, and you can sort of measure this nasal breathing using what's called a nasal cannula, which has a pressure transducer in that. And the question is can we synchronize this to the specs during data capture and demonstrate whether there's a good correlation? Are you able to measure the breathing and the flow by having these devices on the person here? And we were very fortunate that we had collaboration with Gordon Drummond, who's at Edinburgh Royal Infirmary, and we were able to demonstrate that there was indeed a very good correlation. You know, for instance, you have the cannula, which is blue in this case, and then in the green that you have the you have the angular rate, which is estimated by the Spec device. Now that seemed like an interesting thing to do, because and then we ran a number of clinical trials with Gordon Drummond, and we got some good results there, which let us progress sort of further. I'm kind of running ahead of myself. Now, why is this interesting? This is interesting now because you can now have a wireless patch on the person which measures the rotation of chest wall. So you're measuring the breathing rate and flow. And you can process this data locally to see whether it's going abnormally high. And you can transmit this data wirelessly through a base station and connect it to the internet, to the hospital computer. So here you have a way in which you can monitor something like a respiratory rate remotely. And this feeds into the idea that you can have what is known as telemedicine, where you're able to monitor the physiological conditions of patients remotely. So here's an example which traveled quite a long way from motion capture and animation and various other things, and it's ended up here. But that's the nature of research. And what is really fantastic about this is that you're able to do it without compromising very much on the quality, while at the same of the data, at the same time being able to have all the advantages that comes from size and unobtrusiveness. And we can actually, this work was done in the Royal Infirmary by monitoring the breathing of patients after a major operation where they've been given an opioid, which means that one of the side effects of the opioids is that it depresses the breathing. And this is what is known as the central nervous system depression. And if you were to combine, say, the nasal cannula that we used previously as the gold standard against which to compare the specs, but if you use that in conjunction with the spec in the abdomen, because what the spec in the abdomen is doing is measuring the effort, whereas what the nasal cannula is doing is measure the flow of gas, as it were, through the nostrils. By combining the two, we're able to show that actually, due to central nervous depression, both of them go down, or in the case of a physical obstruction in the upper airways, and the physical obstruction could be a number of different reasons, that we're able to demonstrate that the effort is being made in the abdomen, but there is no gas flow coming out. So there are examples here where there is progressive obstruction sort of taking place, where there's a huge effort from the part of the patient, which kind of relieves that, and it goes back to normal breathing. And you can see that the flow resumes and it goes there. So the flow goes low and then it goes up, which correlates with increased effort that you have here. So these are sort of examples of being able to monitor the patients using devices which are in some, at least the spec devices are unobtrusive. I'm not sure about the nasal cannula in this case. And then Gordon has been actually taking this further and not having one device, but having two devices in them, and being able to visualize so this is nasal pressure here, and what you have is the axis of rotation changing over time. And during the inhalation and the inspiration, the expiration process, being able to see what is actually happening to the muscles in this case, what is the direction in which they're moving and which muscles are actually involved in the process. So it gives us a deeper understanding of the process of breathing, which in turn would inform the researchers as to what is really happening during the breathing process, and if there are problems, how can we sort of relieve them. And we take this one step further and said, if you have patients with what is called compulsive obstructive pulmonary disease, called COPD, which is really emphysema or chronic bronchitis, and you want to monitor these people at home, and can you measure the activity along with the breathing? So here's a single device. It measures activity, measures breathing, does the processing in situ, and then transmits this information if needed, because these are programmable, over the wireless to the hospital computer, so that you can monitor remotely the people who are having difficulties, problems, and maybe attend to them and actually nip this in the bud. And quite often the intervention can be simple, such as informing them that they have to take their inhaler, or they have to take their steroid, whatever it is that they are failing to do. And by doing that, you are avoiding admission to the hospital, which is a very expensive resource. So here's an example of how technology such as this can help the healthcare services. So we can make an impact of our research in the real world. So this shows an example of what's happening here. And this is some ongoing trials which is taking place, which measures the activity level. And as the activity level goes up, you can see that the respiratory rate also goes up there. And so you can correlate these things and come up with a scorecard. What are the different indicators which give you some idea as to whether the person is deteriorating or is the condition improving using this technology there. And you can get information such as the number of coughs, for instance. So that could be used as one of the indicators as well. And you can also give overall activity. And these are the publications based on that. Then we come to something which, when you think about this, is a very interesting problem, which is the monitoring of respiration during speech. And this is collaboration with Professor Alice Turk, whose interest is in speech generation. And we know that there are a number of muscles which are active during speech, because normal breathing looks very different from speech breathing. And you want to try and understand which are the muscles which are active during speech breathing. And for instance, if you are taking an in-breath, so you take an in-breath of air, and then you have a speech episode, and you are sort of breathing out this air over a period of time, and then you find, quite unconsciously you do this, you find a period when you can inhale some break in the sentences, and then you exhale over a period of time. Now, that's been, I was going to flip through this in the interest of time. That's been studied in Edinburgh in the 1950s by Peter Ladefoged and his colleagues. And this is a classic paper from 1959, which is again replicated in 2001, which was done by actually having these electromyograms. So these are needles which go into the muscles and then measures the electrical activity in the muscles. And these are the various muscles that you have here, which is the internal intercostal, external intercostal muscles. And this is a classic paper where they actually were able to look at the muscle activity during a speech episode. So it was done in the 1950s. It was replicated again. Ladefoged was quite an interesting person, because if you had seen My Fair Lady, he was the consultant, the speech consultant for My Fair Lady, and you can actually hear his voice in some of the recordings in there. So a challenge for us was, could we replicate this kind of work without the use of these invasive needles in the person? And what we have is a collaborator from France, Didier, and these are some experiments that have been running in December. And what you see are in this case, both the various intercostal muscles. You have the EMG in this case, because that is the ground truth for us. But you also have the specks, which are at the same location. So you have a network of specks, which is natural for us, because we always think in terms of network. And the question is, and you have lots of other things. So he was actually enjoying this, I promise you. You have a Mototachograph, and you have specs, and you have surface EMGs. You have that in 3 muscles of inspiration: the diaphragm, the scalene muscles, external intercostal, and then you have 7 specs. So this is a major piece of work which is still being analyzed, because the data, there's huge amounts of data which will be analyzed. And the hope is that we'll be able to replicate these results using specs. And it's very pleasing to see some work which is done in the 50s coming around to a full circle and being possible thanks to technology which was developed in the School of Mathematics. So I'm going to skip through this and show you some practical applications of this. Now, one of the issues here is some work that we've been doing with Bob Worley, who is a clinical psychologist. in Eden Hall Hospitals in NHS Lothian. And he works with patients with Asperger's syndrome. Now, this is a condition where they have very high IQ, they're very intelligent, but their social skills are not as well developed. And one of the ways in which it manifests itself is that if there is a topic they're really interested in, then they're very happy to talk about it, but they don't know when to stop or give a turn to someone else. So if you have a conversation with Asperger's people, then what you'd like to do is to present them with data and being able to analyze the data as to when is it that they took an in-breath, okay, to prepare to talk, when someone else is taking an in-breath, prepared to talk, but hasn't been given the turn. And we want to be able to do it in a way which we don't bring them to a studio and do this, but have one of these respire devices on them and have several people with the same device so that any instances of in-breath which is not followed by a speech episode is an example where someone wishes to say something, but the Asperger subject hasn't taken the cue and hasn't allowed them to take a turn. So that's the thing. And let me see if it actually works here. So you will see a snippet of conversation, which might not be loud enough, but I mean, that's less important. What is important is we're able to, you have subject 1, subject 2, and then the moderator, and we can actually identify episodes where each of these subjects is talking, and we can identify the in-breaths in these people, and also episodes where an in-breath was taken but not followed by a speech episode. And by being able to do that, we can analyze. There's the only time there's going to be a graph in this, because there's no other way in which I could show this, is you can see what are the number of speech episodes by subject 1 and the moderator, and the in-breaths with no speech. So we can present this data and see whatever the kind of help or treatment that they're being given, is it being effective? Can we quantify this? At the moment, it's done in a subjective way by observation. But here's a way in which we can quantify this. And there's something that I didn't mention, but we can also use these to monitor the environment, and there are a number of projects involved in that. So just to conclude, I just want to draw some connection with where we sit with relative to a number of other works. So one area is what is called tangible computing, where you have a closer coupling between the physical and digital worlds, where you have these devices which perform computing on these devices. So you're blurring the distinction between input and output. The examples of that are, a good example of this, which came out of the Royal College of Art, is what's called a marble answering machine. But if you ever try to use an answering machine and how difficult it is to actually manipulate that, is that what you have is a physical instantiation of a message which has arrived for you, and in the form of a marble which comes in, and the marble is deposited up a tray. And you play it by taking the marble and depositing it down rather than manipulating switches and various other things. So, and then you recycle the marble by dropping the hole. So here's an example of the kind of work which is very useful. And I would kind of draw on that. And another one is called Live Wire, which is done in Zero Park again, where the amount of traffic in the internet can be measured by a wire which sort of moves by a motor, sort of moves a wire. So here are examples of effective computing, of tangible computing, which we believe something like specs can help foster, can actually push forward, because especially the kind of links that we're drawing with the design community, and these are kind of areas that we'd like to sort of explore in the future. And also this idea of small devices, but having a large number of these devices, where these small devices have a task which is very local, but you're combining the effect of these tasks locally in order to produce an effect which is much larger than these very simple devices. And you can see these ideas in other places. And one which I was thought about is this idea of pointillism in art, which was a movement in 1880s onwards, where Van Gogh and Seurat were people who do it, where they have small dots in there, and these dots combine of primary colors, which actually combine in the brain. But what you get is an overall effect, which is far greater than what you'd expect with just a collection of these dots. So you can actually see some of these detail with constituent colors coming out. So that's, in a sense, what we're trying to do with speckled computing has analogies here, is these are simple devices with limited possibilities, but when combined with large networks, the effect that you have is far greater than you would anticipate. But what's the grit in the oyster? What is it that we need to be concerned about? I think, as a technologist, you would think that, oh, this is wonderful, this is great. Why don't we all get this? But I think there are a number of pitfalls as a community, as scientists, that we need to highlight. And one of those is, are we moving towards this world of this, what Bentham called a panopticon? He had this, and it has to be, I mean, you can't blame Bentham for that, because at that time, being jailed was punitive, whereas what he wanted to do was having something which is corrective. And the way he did that was a panopticon, where you have a jail where a single person or a small number of people could view everyone around, but the inmates couldn't see the controllers. And you see this in 1984. You see this kind of ideas elsewhere. With all these devices on the people, on the person, the information that we can gather about people. I'm concerned. I would be worried. So we need to look at the social impact of these kind of devices. And it's wonderful to say how great they are and how interesting it is to work in these areas. But if they're going to hit the real world, there are a number of social questions, societal issues that need to be considered. And so people have asked me, where did the speckled computing come from? Where does the name come from? So the annus mirabilis for us was 2002. It wasn't 1963, it was 2002 for us. And this sort of comes to personal, but 2002 was the year when the four collaborators actually first met in the Far East somewhere. But I was on a holiday in the Cotswolds, the family, in the Cotswolds Summer Park, the water park. It's a very hot day, and the children were much younger, were playing in the pool, in the lake there, which led to all kinds of other problems. They all fell ill. It's a different story altogether. And then there's the idea, I needed to call this something. The idea came, I mean, the other big project in Berkeley that we were competing against was the smart dust. You know, I couldn't call it dusty computing, it didn't make sense. Somehow on, it was a very hot summer's day, I had a newspaper next to me, and then this idea of specs, and then, okay, a network of specs will be a Specknet, and the computation on that will be speckled computing. So that's the origin, which on the personal note, which I would like to say is, speckled computing is not a very popular word at home, because that has taken me away from the family many occasions, but sometimes I like to dedicate to the family because they have borne the brunt of speckled computing. Thank you very much. Thank you.
Thank you, Arvind. That was absolutely splendid. Thank you. I thoroughly enjoyed it. And I should introduce myself. I'm Leslie Eloise, and I'm head of the College of Science and Engineering. And I wouldn't pretend to have understood every word you said, Arvind, but probably every third word. So thank you very much on behalf of us all. I thoroughly enjoyed the lecture. I think, let me explain to you all that I first worked with, well, I worked alongside you, Arvind, many years ago in the Far East when we went recruiting on behalf of the university. And Arvind started to explain some of these thoughts to me about what he was doing. And it's been wonderful to come full circle now, to come back here, Arvind, and hear the results of all your work over the many years. I think what has been fabulous for me is to see how many different areas that your specs can aspire to, how many things that they can help us develop on. From golf swings, and I don't think we'd better put specs on my golf swing, because I don't think they could be analysed, all the way through to gait analysis, to animation, to health, etc. It's just, I think the world's your oyster. And I think we all look forward to seeing just where you take your speckled computing and your specs to next. So on behalf of us all, I'd like to thank you very much for a wonderful, inspiring lecture. And to say to all of you, this happens at every inaugural lecture, but we actually have some food as well as some drink afterwards. So there's a fork supper, but that's really to thank those of you who have been at the workshop, and those of us who have not, we'll just join the food and the drink anyway. And during this time period, I hope you'll all come and speak to Arvind about what he's doing and his wonderful work. But join me in thanking him. Thank you very much indeed. Thank you.
This production is brought to you by the University of Edinburgh.